Sure. Okay. So I guess the first thing I would do is I'd look to see if there's any algebraic thing I can do. I notice this fraction can reduce because I have a factor of cosecant on top and a factor of cosecant on the bottom. So we do that. And using one of my cofunction identities, I can rewrite tangent of pi over 2 minus x as cotangent x. Okay, there. And then I would say, let me just check something real quick. I should check there. Decide which one I want to do. It shouldn't really matter. Okay, good. Let's do that then. So I'm going to think about this as two separate fractions. So cotangent x times 1 over cosecant x. Because I'm going to use one of my quotient identities to rewrite cotangent as cosecant x over secant x. So that I can cancel those out. And then I know that 1 over secant, I can use one of my reciprocal identities to rewrite that as cosine. And that's as far as we can go because we've got it to a single trig function. Sure. Was that the only way you could have done that one? Lordy, no. There's lots of ways you could have gone about approaching that. But that's the way that I thought was the obvious way of doing it. There's probably several others that are pretty much equivalent. Anybody else? About 1 through 14 here. Yeah, Mackenzie. 10? Okay. So the first thing I'll do here is I'm going to look to see if there's anything algebraic to do. And I see that there's a greatest common factor of tangent here. So I think I'll start by factoring that out. I think this one could potentially get very messy depending on how you attempted to go about doing this. But this is going to be pretty quick if you take that as your first step. And then I recognize 1 over cosecant squared is sine squared, just using one of my reciprocal identities. And similarly, 1 over secant squared is cosine squared. And then, whoa, look at that. Sine squared plus cosine squared. That's 1. So I'm left with just tangent times 1, so I have tangent x. I think depending on how you did that, that could have gotten quite messy, as there potentially could have been a lot of fractions kind of rattling around in there. That makes life potentially, like a little bit difficult. But that way, right there was kind of nice, as I really got rid of the fractions as quickly as possible. So you don't really have to deal with them. Michelle? Mm-hmm. Okay. So I know that there's nothing algebraic to do here, right? Or nothing obviously algebraic to do here. What I'm going to do is I know that 1 is equal to sine squared plus cosine squared. So I'm going to make that substitution. So I have a plus cosine squared and a minus cosine squared. Those will just kind of cancel each other out. That just leaves me with sine squared over sine. Which I can reduce to just sine x. Is that okay, Michelle? Sure. Alex? Sure. So on number 14, what I would do first is an algebraic thing. I would make a common denominator to add these two fractions. The common denominator here, since the two denominators don't have any factors in common, is just going to be the product of the two denominators. So I'll multiply the first fraction by 1 plus sine y. And I'll multiply the second fraction by 1 minus sine y. So the denominator then I'll have 1 minus sine y times 1 plus sine y. So far, so good? Okay. So I see a couple of algebraic things right away to do. In the numerator, I can combine like terms. I have a plus sine y and a minus sine y, so those are going to cancel out. And then I have 1 plus 1, which I can just add to give 2. In the denominator, I can multiply these two things together. I notice that they're a difference of 2 squares, so I could use the difference of 2 squares factoring pattern to multiply them out quickly, or you could just FOIL it out and combine like terms. Either way, you're going to have 1 over sine, or 1 minus sine squared. And notice that this is quite similar to the numerator from 9, where I had 1 minus cosine squared. I'm going to do that same trick by substituting the 1 for sine squared minus cosine squared. Or sorry, plus cosine squared. So I can cancel the sine squareds. Doing so far so good, Alex? Okay. So what I'm left with, I'm going to write as 2 separate fractions. I'm going to really think about this as 2 times 1 over cosine squared y. So I just move the 2 from the numerator, like multiplying it to the whole fraction, just so it'd be easier to see that 1 over cosine squared is just secant squared. So I'm left with 2 times secant squared. Is that okay, Alex? Sure. Mia? Sure. Okay, so it wants all 6 trig functions. The first one, really easy. If I have cosine, secant I basically get for free, right? So nothing tricky about that. It's just the reciprocal of cosine. Next, I'm going to find sine. So I know that sine squared plus cosine squared has to equal 1. So 3 over 4 squared is 9 over 16. When I subtract that from both sides, I have 7 over 16. And when I square root both sides, I have that sine theta is plus or minus root 7 over 4. Now I just need to decide whether this is positive or negative. So I know that cotangent theta is cosine, which is positive, over sine. Maybe I'll just write it. And I know this whole thing is negative. Well, I know the cosine is positive because it's 3/4. That means that sine needs to be negative, right? For that fraction to be negative. So there's sine then is negative 7 pi over, or square root 7 over 4. And since I have that, cosecant then is just going to be the reciprocal. You would want to rationalize that denominator. I'm just going to leave it for now, though, and leave that part to you. And then to get cotangent then, I'm going to take cosine, divide it by sine, so again, I get negative 3 over root 7. Should rationalize that denominator. I'll leave that part to you. And then tangent should be its reciprocal. So negative root 7 over 3. And that's that. Does that feel okay, Mia? Sure. So just kind of finding one of them and then just using the reciprocals to kind of get everything else. Alex? Sure. So secant theta is 1. I know immediately its reciprocal is also 1, right? Cotangent being undefined. When something is undefined, you have something divided by 0, right? So that tells me that tangent is going to be 0 over something. Well, that's just 0, right? Okay. So if I use the Pythagorean theorem then, I know that sine squared plus cosine squared has to equal 1. That just tells me sine is 0 then. I don't need the plus or minus because sine squared is 0 also, so cool there. And then the reciprocal of that is going to have 0 in the denominator, so that's undefined. So that's everything, right? Cosine is 1, sine is 0, cosecant is undefined, tangent is 0. That's the other 4 that they didn't give us in the problem. Is that cool, Alex? Sure. What to do with the undefined is maybe not totally obvious, right?
Yeah.
Yep. The trick is just remembering that undefined means you divide it by 0. So, Tyler.
You do number 2.
Sure. So I'm going to be using the, let me just double check the number on it. I'm going to be using the second Pythagorean identity because it has cosecant and cotangent in it. So I have 1 plus cosecant squared is going to equal cotangent squared. So we have that cotangent is going to be plus or minus the square root of 10 then, right? Okay. And because we know cotangent is positive, we really know it's positive root 10. Cool? Okay. If I look at my identities, I also know that cotangent is cosecant over secant. So if I multiply both sides by secant alpha, I have that cosecant alpha equals cotangent alpha times secant alpha. Oh, shoot, we should probably, and then I'll divide, we're looking for secant, so I'll divide both sides by cotangent then. Cool with that? So I took this equation and multiplied both sides by secant to get to this. And then I took that equation, divided both sides by cotangent to get to that. And that's helpful because I know cosecant is -3, and I know cotangent is root 10. So all I would need to do is rationalize that denominator, and we've got ourselves our secant. Is that cool? So I just rearranged that cotangent quotient identity to get the cosecant by itself, or the secant by itself. Does that feel okay? You probably could have used the other Pythagorean and sorted your way through that also if you wanted to go that route. That probably would have worked out also, since you have cotangent, and would have been able to give you you would have been able to get tangent out of that. You could have gone that route also. Okay. Any last questions on this homework? Great. We can always come back and talk some more. But let's start the next section here today. So we're going to be talking about solving trigonometric equations today. So we've done a little bit kind of regarding this already in last chapter, right? So in last chapter, we would have asked you to do like a problem like this. So we could have asked you to do like find the exact value for sine inverse 1/2. So to do something like this, you would have recognized that the range for sine inverse is negative pi over 2 to positive pi over 2. So you're looking at things in quadrant 1 or 4. Clearly, sine is only positive in quadrant 1. So we're just going to go to the unit circle in quadrant 1 and look for where the y-coordinate is 1/2. And you would have concluded that the value there should be pi over 6. So this is just like a problem we would have done in last chapter. Here, what we're going to do is we're going to ask you to, say we're going to solve for x for sine x equals 1/2. And this also kind of looks like a question from last chapter, but you're missing a part of this question if it was a last chapter question. What part are you missing? What additional information would we have given you in the last chapter if we asked you to solve a question like this?
Would have given us like kind of like a range.
Yeah, I would have given you an interval of x to solve over. Okay, here I would have given no such interval. Okay, fine. So how many answers is this going to have?
2.
More.
Would be 4.
More.
6.
More.
12.
Infinitely many. Infinitely many. Let's kind of demonstrate why. So if we think about this graphically, that's kind of the easiest way to demonstrate what's going on here. So this is our graph of sine, right? This is our line, y equals 1/2. How many times are those two graphs going to intersect? Infinitely many, right? Because the graph keeps going up and down, crossing that line of y equals 1/2. So like I have a solution here and a solution here, a solution here and a solution here, a solution over here and a solution over here. So is there any kind of relationship between these solutions that we're seeing repeated over and over and over again? Yeah, how far apart, say, are these two solutions?
Period.
Yeah, they're one period apart. That's correct. So if you look at like this section of the graph, that's one period, right? Similarly, these two solutions, also that same one period apart. Or if we looked at those two solutions are one period, as well as those solutions are one period. So really, there's kind of two different types of solutions, right? There's those solutions that we've drawn in green that are all one period apart, and the solutions I've drawn in gray that are all one period apart. Do you guys kind of see that?
Yep.
Okay. So let's talk about how algebraically we get there. So we would start by doing the sine inverse to both sides to get the x by itself. Then I'm going to go to the unit circle and look for all the places where y is 1/2. That happens at pi over 6, as well as 5 pi over 6. So in our picture here, pi over 6 is that one. And I guess I probably have to use this color. And 5 pi over 6 would have been that one. Everybody okay? Still doing all right? So how are we going to represent the infinitely many solutions that are all like a period apart? So what I'm going to do is I'm going to write pi over 6, and then I'm going to write plus 2 pi k, where k is some integer. What I'm really saying there is pi over 6 is a solution, and then anything coterminal to pi over 6 is also a solution, right? Because if k is an integer, that's a positive or negative whole number. So it means that anything where we've added or subtracted some multiple of 2 pi from pi over 6, still a solution, right? We go 2 pi, that's a period. Hit another solution, go another 2 pi, still a solution. Another 2 pi, still a solution. You guys buy that? And we can do the same thing with the 5 pi over 6. So that's how we can represent infinitely many solutions. We just find our solutions on the unit circle, and then we tack on that plus 2 pi k on at the end, and we're done. So that's not too bad, right? Now, these infinite solution representations that we've given here can be really useful. Let's say hypothetically on this problem, instead of asking you basically to solve this over all real numbers, we gave you some kooky interval. Like, let's say that we wanted the x's from, I don't know, negative 5 pi over 2 to 11 pi over 2. Notice that's way more than one trip around the unit circle. That's way more than one period, right? This is basically negative 2.5 pi and 5.5 pi. Sometimes it's easier when you have the fractions like that to think about them as decimals. Okay, so what are we going to do here? To solve this, I'm going to be using my infinite solution. So I'm going to start with like the unit circle solution. And I'm going to subtract 2 pi from this until I get something that's smaller than negative 2.5 pi, in which case I'm going to stop. And then I will add 2 pi to pi over 6 until I find a solution that's bigger than 5.5 pi, in which case I would stop. And at that point, I found all the things coterminal to pi over 6 that are inside of this interval. So if I take pi over 6 and I subtract 2 pi, I get 11 pi over 6. That's still bigger than negative 2.5 pi. So I'll subtract 2 pi again. That gives me negative 23 pi over 6. That is too small, though, right? That's almost negative 4 pi. So I'm going to discard that solution. So I found all the negative solutions that are coterminal to pi over 6. So now I'm going to add 2 pi to pi over 6. 13 pi over 6. That's still less than 5.5. So we'll do it again. 25 pi over 6. That's still less than 5.5. So we'll add again. 37 pi over 6, that's too big, right? It's a little over 6 pi. So we found all of our solutions in that interval that are coterminal to pi over 6. We'll do the same thing for 5 pi over 6 now. So subtracting gives me 7 pi over 6. That's good, still bigger than 2.5. I do it again, I get negative 19 pi over 6. That's a little less than negative 3 pi. That's too small. I'll discard that one. And now we'll start adding. So that's 17 pi over 6. That's still less than 5.5. Add again. 29 pi over 6. Still less than 5.5. I'll add again. 41 pi over 6. That's almost 7 pi. That's way too big. So my solutions there are the ones that we have left in blue. So you can see that the infinite solution, even if you're not asked for an infinite solution, can be really useful if you're given like a weird interval in which to solve over, right? Is everybody okay with how we're using that? So that's the trigonometric idea. Let's look at some weird algebraic things that can happen now that can make some of these solving problems a little bit more difficult. Does that sound okay to you guys? But you guys have the trigonometric idea? Okay. Let's do some examples then. So for these examples, we're just going to solve for x on the interval from 0 to 2 pi. Note the interval there, we have a bracket at 0 and a parenthesis at the 2 pi. What is the bracket versus parenthesis? Those mean two different things, right? The bracket means that number is included, so 0 could be an answer. The parenthesis means that number is not included, so 2 pi cannot be an answer. Everybody good? As a reminder of what those mean. Let's do some examples here. So let's say we have cosine squared x equal to 1. Can I go ahead and apply cosine inverse right away? No, why not? Because I have cosine squared, right? So what do we have to do first before I can do the cosine inverse?
Get rid of the squared.
Great. And how do we get rid of a squared?
We use the Trigonometric, right?
Nope. Easier than that. Think back to last year. If this was x squared equaled 1, what would you do? That's what we'll do here. Now, when we square root both sides of an equation, what do we have to be wary about? Or what do we have to remember happens?
Everything gets square rooted.
Okay, everything gets square rooted, sure, but plus or minus. as a little aside here, I will say that in my experience, the problem that students have with solving these things is not the trigonometry part, it's the algebra parts. So it's like forgetting some of these plus or minuses or doing some other algebra things incorrectly. So I'm going to separate that into two equations then. So I'm going to solve cosine x equals positive 1 and cosine x equals negative 1. So I can apply the cosine inverse to both sides of each equation. So far, so good. To evaluate cosine inverse of 1, I'm going to go to the unit circle and look for the place where the x-coordinate is equal to 1. That happens only at 0. And then again at 2 pi, but 2 pi is not a valid answer for the interval that we're solving on. So I won't bother to write that down. Everybody's okay with that? In the other equation, again, to evaluate cosine inverse of negative 1, I'm going to go to the unit circle and look up where x is equal to negative 1. That happens at pi. Now, as a hypothetical, if instead we had been asked you to solve this over all real numbers, we would just take these two answers and tack on that plus 2 pi k to the end, right? Everybody's okay with that notion? I want to point something out here because there's actually a simpler way to write this answer. If I look at that first solution, it's going to include things like 0, 2 pi, 4 pi, 6 pi, 8 pi. If I look at the second solution, that's going to include things like 1 pi, 3 pi, 5 pi, 7 pi. If I write those all in a row, I'd have like 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. How far apart are all of those answers? Just pi units, right? So I could really just kind of simplify this down and combine these two solutions into one, doing 0 plus pi k. Now, on your test or whatever, I wouldn't mark you down if you did not do that, for the record. If you're looking at the answer keys, I will assuredly have done that on the answer key because it's way less writing to combine answers if you're able to do that. And there's some problems where doing this combining can make your life a lot easier, where you're just dealing with, you reduce the number of steps you have to do later on. But I wanted to kind of show you that that's something that can happen here. The specific example we were working through was just solving it from 0 to pi, which we had done in the red. This is just like a hypothetical because it's a good chance to illustrate that this, how you can combine two infinite solutions into one. Sometimes. You're not always able to do that. Does that feel okay? So I'll point that out a couple of times where it might happen. And I'll show you guys an example later on where doing this actually reduces your workload a little bit. Let's look at another. So again, we're still solving over 0 to 2 pi. Here we have 2 cosine squared x plus cosine x minus 1 is equal to 0. Can I just apply cosine inverse to both sides to start this up? No way, right? Like, that's a crazy idea. Because we have, you know, a cosine squared, we have a regular cosine, and we have a -1. Yeah. What should I do with this? Any ideas? Oh, thank you. Well, what if instead we had this equation? 2a squared plus a minus 1 equals 0. Would you know what to do with that? Mia? So this is a quadratic equation, right? To solve a quadratic equation, one technique we might use is factoring. Is there any other techniques we have to solve a quadratic? There's one more good one. The quadratic formula also could be used here. Either is going to be okay. This one is factorable. That's the method we're going to use because it lets me review factoring with you guys right away. And note that this is really the same problem as before, where I've just taken all my cosine x's and replaced them with a's, right? Okay. So there's two different types of quadratic factorings that we've run into. There's one method where the leading coefficient is 1, and there's another method when the leading coefficient isn't 1. Which case are we in here? What's the leading coefficient this time? The leading coefficient? 2, which means that we're going to have to do like the longer version of factoring. So what we're going to be looking for is two numbers that multiply to give us the leading coefficient times the constant term. And also those two numbers should add to give us the leading or the coefficient on the linear term. So what are the two numbers that multiply to give us -2 and add to give us +1? 2 and -1. Very good. Now, these two numbers do not take me straight to my factored form. Since the leading coefficient isn't 1, what these two numbers do is they describe to me how to break up the linear term into two pieces. Notice that 2a plus -a or -1a is still just a, right? So once we've broken our trinomial up into 4 parts like this, we're going to make 2 groups. From the first group, we can take out our greatest common factor of 2a. When I factor out that 2a, what's left?
You have a squared, or a, and then you have 1.
A plus 1. If I look at the second group, what's the greatest common factor I can take there? -1. And what's left?
You have a, and then 1.
A plus 1. Notice that each of these two terms has an a plus 1. So if I factor that out, I'm left with 2a minus 1. Everybody cool on how we factored this? Again, we did this a lot last year. We should hopefully remember doing this. And while totally fine to not remember all the details after a year, after seeing an example, it should all come tumbling back here, and we should hopefully remember how to do this pretty well. So at this point, I'm going to go ahead and put the cosines back. So once we have our quadratic equation factored. If we wanted to solve this, what do we do next? Does anybody remember what to do next? Oh. Okay. We apply the zero product property, which allows us to set each factor equal to 0. As a reminder, the zero product property only applies when you have something factored equal to 0. If I had factored this and it was equal to 1, it doesn't allow me to do this. This is purely reliant on the fact that if you multiply two things together and you get 0, one of them has to be 0. I should say at least one of them has to be 0, right? Okay. So now I can just go ahead and solve these two separately. The first equation, I can subtract 1 from both sides. Then apply the cosine inverse to both sides. The second equation, I can add 1 to both sides. Divide both sides by 2. And then do the cosine inverse to both sides. So for the first equation, to evaluate cosine inverse of -1, I'm going to go to the unit circle, look up where x is equal to -1. That happens at pi. We'll go to the unit circle and look up where x is 1/2. That happens at pi over 3. And also at 5 pi over 3. And those are my solutions. So you see on this part, or on this one, the algebra was really the complicated part, right? The trigonometry piece wasn't so bad. All we did was had to look some pieces up off the unit circle and we're basically finished. But we had a lot of factoring to kind of handle before that. I think we're on C. Again, we're still solving from 0 to 2 pi. What do you notice that's different about this one than the previous ones?
There's 2x instead of just x.
Yeah, we have a coefficient on our x, right? Do you think that makes a big difference?
I don't think it does, but I think you're going to say it does.
Okay. You would think it wouldn't, right? You go, okay, well, I can just do this as I would normally, right? I'll do the sine inverse of both sides. So I'll go to my unit circle, look up where y is 1/2. So that happens at pi over 6. And it also happens at 5 pi over 6. So I just divide both sides by 2, and I should get pi over 12 and 5 pi over 12, right? No. Unfortunately, we've missed some answers. Wait, what? Mr. Kulik, you're telling me why? Where? How? We did the exact same thing we've been doing. Right? That doesn't make any sense. Let me explain. So remember back to chapter 3 when we talked about graphing these trigonometric things. This part is what the 2 is, right? how did that coefficient affect this graphically? How does that 1 over b part, or in this case a 2 on our x, affect the graph of this equation?
Oh, it affects the, like the horizontal stretcher.
Great, it performs a horizontal stretch or shrink. And what attribute of the graph does that change?
Makes it look longer.
So it'll change the period, right? By making the graph longer or shorter. Hi. Thank you. It's for you. So if the graph's period changes, perhaps we have more than one answer, or more than just these two answers between 0 and 2 pi. Right? Does that feel okay? So this is going to be the fix. Okay? This is the fix. So when we apply, or when we go to the unit circle to pull our values, we're actually going to perform this with infinite. We're going to actually find the infinite answer here. So this is going to be plus 2 pi k. And this piece is going to be plus 2 pi k. Everybody's doing okay? So that's not a big change. Here's the catch. When we divide both sides by 2, we also have to divide the 2 pi k by 2. So again, if we're solving from 0 to 2 pi, I know that if I have pi over 12, if I subtract pi from that, I'm getting a negative value. That can't possibly be my solution. So pi over 12 is the smallest answer I can have. If I add pi to that, I get 13 pi over 12. That's still less than 2 pi. If I add pi to that again, I get 25 pi over 12, and that's bigger than 2 pi. So discard that. 5 pi over 12, if I look at that solution, if I subtract pi from that, I get negative, which is too small. So 5 pi over 12 is my smallest answer for that solution. If I add pi to that, I have 17 pi over 12, which is still less than 2 pi. If I add pi again, I get 29 pi over 12, which is too big. So I actually should have these 4 solutions. So that's the trick. Whenever you see a coefficient on the x, you need to always find the infinite solution and then use that to generate all the solutions that lie in your interval. That's the easiest way to handle it. Because if your interval is not 0 to 2 pi, this can become really difficult to do any other way. Does that feel okay? Let's do another one like this to make sure we got the idea. So let's say cosine squared 3x is equal to 1/2. What do you guys want to do first on this one?
Square root.
Yeah, we'll square root both sides. So what do we have to remember when we square root both sides?
Plus or minus.
Plus or minus. Okay, when I square root 1/2, the square root of 1 is 1. And then I'd have 1 over the square root of 2. I'm going to rationalize that denominator right now and just write that as root 2 over 2. Everybody's okay how square root 1/2 became root 2 over 2? Okay. Yeah. Yep. So we'll split that into two equations. So I have cosine 3x equals positive root 2 over 2, and cosine 3x equals negative root 2 over 2. So I'm going to go to the unit circle and look for where the x-coordinate is root 2 over 2. That happens at pi over 4 plus 2 pi k. And then also again at 7 pi over 4. Again, same idea for the other one. So where the unit, or where x is negative root 2 over 2 is at 3/4 pi, and then plus 2 pi k. And then as well at 5 pi over 4 plus 2 pi k. Everybody feel okay to hear? Notice I'm doing the infinite solutions because I have a coefficient on my x. So divide both sides by 3 in each of these. It's going to be pi over 12 plus 2/3 pi k. And I'm going to leave a space underneath it to do for where I'm going to generate all of my solutions. And now here I'm going to write this as 3 pi over 12 or 3 pi over 12. I know I can reduce that, but turns out it's going to be like a little bit more convenient if I don't do all my reducing until the very end. That way I don't have to mess with like a bunch of different common denominators. I just would prefer to have the same common denominator like everywhere, so I don't have to like make the fraction arithmetic harder than it needs to be. But I recognize that yes, 3 pi over 12 you could reduce. If you wanted to do that now, that's okay. I'm going to choose to do all the reducing at the very, very end. Okay. So I'm going to acknowledge that 2/3, when I make a common denominator with 12, is just going to turn into 8 over 12. And again, we're solving from 0 to 2 pi. So I have pi over 12. I have 9 pi over 12. I acknowledge I could reduce that. I'm just not going to do it right now. 17 pi over 12. And then 25 pi over 12, which is too big. And again, I acknowledge I'm not going to do any subtracting because 8 pi over 12, if I subtract, it's going to be negative, right? For all of these. So I'm not even going to bother with checking the negative ones because I did it right now. All of my base solutions are smaller than 8 pi over 12, right? So next one, 7 pi over 12. 15 pi over 12. I acknowledge I could reduce that. I'm just not going to do it right now. 23 pi over 12. And then 31 pi over 12. But oh no, that's too big. So 3 pi over 12, I know I can reduce that. 11 pi over 12. 19 pi over 12. And then 27 pi over 12, that's too big. So 5 pi over 12. 13 pi over 12, 21 pi over 12. I acknowledge I can reduce that. I'm just not going to do it right now. And then 29 pi over 12. Oh no, that's too big. So those are my solutions. When I write my final answer, I would go back and reduce each one of these ones, but that's the gist of that. Is everybody okay there? I know, man, I know. All right, let's do another. Yes. Those are ones that would need to be reduced.
Oh, okay.
So if you're looking at my final answer, it wouldn't actually read those. Those ones would be the reduced ones.
Okay, thank you.
But I just didn't feel like rewriting. I didn't leave myself enough space to like write the reduced version there without it being ugly. So I just was pointing out that those need to be reduced. That's all. Okay. Okay. Here's a new one. I know. Tan 2x times sine squared 1/2 x equals tan 2x. What do you guys want to do first for this one?
Square root. Or no. If we get tan 2x on the other side.
Yeah. So that is what you'd want to do. What you do not want to do in this case, that is very tempting, and is typically the first suggestion I get, is divide both sides by tan 2x. While that would enormously simplify the problem, why wouldn't you want to do that? Since tan 2x has a variable in it, can it equal 0?
Yeah.
Yeah. In which case you're dividing by 0, right? Which means you're going to be losing solutions. So you do not ever, ever, ever want to do that unless you've thought really carefully about the possibility of the thing you're dividing by cannot ever equal 0. So instead, as Paul suggested, we'd want to subtract the tan 2x to the other side. Notice I can't subtract that from the other term because they're not like terms because of the sign squared attached to it. So I just have to kind of write it next to it like that. Feels okay? What now?
Factor.
Good. What are you going to factor?
So I would switch everything to A, right? That seems simpler.
Well, you have two different kinds of trig functions there.
Right.
So you need like A and B if you want. Okay.
That help. That helped me.
Okay. I see a greatest common factor. So yes, I'm going to factor, but not like a quadratic. Instead, I'm just going to take the greatest common factor off
Oh, I see.
and do that. Which has now separated the tangents and the sines basically into two separate problems, right? So I'm going to go and apply the zero product property now. Which is way better, right? So in the first equation, we'll do the tan inverse to both sides. So I'm going to go to the unit circle and look for the place where y over x is 0. Or really just where y is 0. So y is 0 at two places. It's at 0. And then also again at pi. Divide both sides by 2. Oops, forgot to write what k is. I mean, we all know, but should still be there. Yes. No, I'm looking anywhere.
Oh, so it could be on the entire unit?
Yes. Yes, I'm looking for all the places on the unit circle where this is happening. Yep, good question. Now look at these two infinite solutions. The first set we have 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, right? On the second set we have a half a pi, 3 halves pi, 5 half pi, 7 half pi, or really a half a pi, 1 and a half, 2 and a half, 3 and a half, 4 and a half. If I line these all up together, I'd have 0, a half pi, 1 pi, 1 and a half pi, 2 pi, 2 and a half pi, 3 pi, 3 and a half pi, etc. Notice that we can combine these together. That's going to make life a little bit easier here in a minute. Yes. Well, this is like 0 pi, 1 pi, 2 pi, 3 pi, etc. This one is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. If I line those all up in order from biggest to smallest, I have this. Right? So how much are we going up by? By half a pi. Is that okay? So again, like that part that we're adding each time doesn't necessarily have to stay the same, right? It just, if I can combine it together, it typically makes life a little bit easier when I get to the final step here. So again, if I'm going from 0 to 2 pi, I have 0, pi over 2, pi, 3 pi over 2, and then not 2 pi though, right? Because when the interval we're solving over has the parenthesis at 2 pi. Is that okay to hear? We still have another half of a problem to go, though, because remember way back here we had this other piece that we haven't done anything with. I'll do that so I don't run into this. So add 1 to both sides. We'll square root both sides. We'll do the sine inverse. Oh, shoot, we have to separate this. Excuse me. Then we'll do the sine inverse. Go to the unit circle where y is equal to 1. That happens specifically at pi over 2. And do the same thing. This happens specifically at 3 pi over 2. I multiply both sides by 2. And then I'm going to make the following observation here. So this first solution contains things like 1 pi, 5 pi, 9 pi, etc., right? All of those answers lie there. So I don't need this answer at all. We've already accounted for everything there. You guys agree with that? If I look at this answer, This has things like 3 pi, 7 pi, 11 pi. All those answers also still lie there. So I've already accounted for anything there, so I don't need it. Turns out that that's all I needed. So in fact, dividing by tan 2x would have been a really bad idea, because that's really where all my answers were, was on that part.
Just like repeating answers.
Yeah. Let's stop here.
I still need to write.
Yeah. At this point, you guys could work on the 15 through 42 is the problems part. We also should be aware that at some point this week you should expect a homework quiz. Since it wasn't today, when would you best expect that? Thursday. And what would you expect, what section would you expect this to be on? 5.1, since we've just talked about 5.2 today, right? So don't worry about the solving for the homework quiz, just that first section. Does that feel okay? And you guys can go.